Much, Peter, and it's a great pleasure to be back at the Institute and give a talk, a real talk, first real talk in over 2 years here. I'd like to thank Peter and Alex for giving me this opportunity. The work I'm going to talk about is joined with Bourgain and Sarnak, and it started here at the Institute in 2005 when Alex was running a program on the groups, representations, and discrete mathematics. And I'll say a word about motivation and that history in a moment. Let me start by introducing the Markov equation. There were a number of talks in the first half of the year in the fall. There were talks by Bill Goldman and Will Chen and Peter Sarnak and Alex Lubowski, and I would reference those talks, but I will try to make the talks self-contained. So the first half would be perhaps for many of you a repetition of what you already know, and for others an opportunity to wake up. And then I will present the outlines of proofs in some detail. And by the time I finish at 12:15, I hope you all will be hungry for more. So let me start with the Markov equation. So this is Andrei Andreevich Markov of Markov chains fame, and this is his thesis. Now there is one thing that, okay, before I forget, this came up, I recently discussed this with Bill Duke several weeks ago, and the papers, there are two papers which are published in Mathematische Annalen, and a number of people, in particular Dixon, complain about gaps in the proofs in those papers. Now, the complete thesis is actually published in Russian in his collected works, and also in Russian Math Surveys, I think 1948. And Markov's collected works is quite it was published, I think, in the early 50s. And it's quite a remarkable volume because, well, the papers, in particular, the thesis itself, and then there's overview of his work by Linick and by Delaunay, and then there are references to all the papers referencing Markov's work up to that point. I haven't seen this. So this is sort of, I think, right before Stalin died. So anyway, this is his thesis. So Markov, it's a simple, I will try not to digress too much. I'll keep, Peter will.
If you go away, of course, I'll try.
Yeah, I have to wake up myself. So I'm, and I will try not to make too many jokes. Actually, not any jokes. I'll focus today if I wake up. Anyway, so this is the equation is a simple equation. So Markov triples so positive integer solutions. Markov numbers coordinate of a Markov triple. And there is a notion of a Markov sequence, which is the largest coordinate of a Markov triple counted with multiplicity. Now, always tempted to say a word about his work, which is spectacular and fundamental. Malyshev says that the only paper in the 19th century which is comparable with this is the paper by Riemann. I wouldn't go so far. Anyway, he proved an infinite sequence of theorems Markov. I'll tell you the first two. So there is a result which is usually attributed to Hurwitz, and in fact, Hurwitz did give a beautiful and self-contained proof, but it's already in Markov's work. And this is the following. So an irrational number admits infinitely many rational approximations P over Q such that alpha minus P over Q is less than 1 over square root of 5 Q squared. This is sharp. If alpha is GL to Z equivalent to the golden ratio. The second result is by Markov doctoral advisors, Perkin and Zolotarev. And the following, so this is 1878. And it says the following, so if alpha is not GL to Z equivalent to the golden ratio, then there are infinitely many rational approximations P over Q such that alpha minus P over Q.
Sorry, what's the F of GL to Z here?
So alpha is equal to A beta plus C. No. So if G is A, B, C, D, then linear fraction transformation.
Thank you.
So if alpha is not GL to Z equivalent to the golden ratio, then there are infinitely many rational approximations such that this is less than 1 over square root of 8Q squared. And this is sharp. If alpha is GL to Z equivalent to theta 2, which is equal to 1 plus square root of 2. Now Markov proves an infinite number of these theorems. I'll write down the formula and you'll see what I mean. So J is Markov number, and I will write them down in a moment. 9 mj squared minus 4 1 Q squared. I will not be able to do justice to Markov's work. The paper I recommend is by Bombieri called the Markov tree. And the Markov tree is the following object. So there is one solution which is staring you in the face. 1, 1, 1. And okay, so Markov tree is the following. So there is one solution which is 1, 1, 1. 1, 1, 2, 1, 2, 5, 1, 5, 13, 2, 5, 29, 1, 13, 34, 5, 13, 194, 229, 169, 529, 433. And let me add one more note to indicate that it is 29, 433. 37666. And the Markov numbers are read off from this tree. Oh, you have a nice job. Sorry. I brought. So one is what gives you the golden ratio. 2. So 1, 2, 5, 13, 29, 34, 89, 169, 194, 233, 433.
Sorry?
I think it might be here.
Okay.
Yeah, so what am I doing? If you look at this equation as a quadratic equation in x1, you see that the two solutions are related simply as follows. So if you have one solution, you can obtain another solution by applying what is called Vieta involution. And the same for x2 and x3. So the group generated by these involutions, but there are also permutations, and they will be important in what follows. So the Markov tree can be viewed as an orbit under the action of gamma of the root solution. Okay. Now let me just very quickly review the immediate history following the publication, and Markov's collected works indeed list Hurwitz as the first paper. So the first paper referencing, well, so the first paper referencing Markov's paper is a paper by Hurwitz 1907, where
Is it possible to move the camera?
I can try.
No. Maybe right at the middle board. He's coming. Hang on. Yeah.
It's
Can you use that board, right? Yeah. Okay, it's fine.
sorry. It's really a hybrid tone.
Yeah. We're the leading institution on something. Hybrid talks.
Well, so if the people on Zoom get bored in the first half, they can just tune into another.
I'm sure they are.
And the people in the people in the audience.
No, we have smartphones. We can.
Thank you. That's very comforting. Now, what am I going to do? So the first reference to Markov's. Why am I belaboring this point? The first reference to Markov's paper is a paper by Curvatures where he looks at this equation. So this is so he says I want to find n tuples of integers such that the sum of their squares is divisible by their product. And then at some point he comes to n equals 3 and references Markov's paper. But the motivation for looking at this equation is what I just said. And then in 1913, Frobenius wrote a very important paper called Über die Markovschen Zahlen. He's clearly very impressed with Markov. He says these are very striking results, and nobody seems to have read this paper. Nobody's quoting. He said Minkowski doesn't quote the paper. Curvatures doesn't quote the paper. In the other, and then okay, so he makes a conjecture which is still open, asserting that M is equal to MS. Now, while
You should explain what that means. That means the biggest guy determines the two smaller.
yes, well, I think people will stop me.
I mean, well, maybe now's a good time. Could you explain again what all the notation actually means? Like, I didn't quite follow.
So the Markov triples.
So script M is a set consisting.
No. So this is a Markov triple. These are Markov numbers. Markov sequence is the largest coordinate. So it says that you can get to the largest coordinate in only one way. And that's the content of the uniqueness conjecture, which is open. So the statement that Markov sequence is equal to the set of Markov numbers means that you will not get a Markov number in more than one way by following this tree, the largest entry.
Okay.
And it's not very important for what it's convenient to assume that it's true.
So if we understand that, we can forget the notation.
Yeah,
You're asking me.
You don't need to distinguish between MS and M.
Yes.
So the sequence has a tree structure.
The triples have a tree structure. And the triple actually carries more. So when you, okay, I don't want to go into it, but there is also a quadratic irrationality associated with the Markov, and you read it off from the triple. So the triple carries a set. The triple itself carries a certain arithmetic information, and
you can't go from one point to another point without knowing all three. But if the uniqueness conjecture is true, then it is determined, but not.
So, Spiral, 80 to get to 89, you have to traverse the set of triples, and I don't think I. So one point I should make is that So this is the first paper referencing. This is the first paper referencing Markov's paper. The Markov equation itself appears in the work of, I think it is implicit in the paper of Poincaré in 1884, and then Vaught 1889, and then Fricke. I think this is 1895. And then Fricke and Klein, 1897. And it appears as a Fricke identity. Well, what is now usually referred to as a Fricke identity. And this is, this will be important in what follows, but so trace square of AB is equal to trace of A, trace of B, trace of AB, plus trace of the commutator, plus 2. So, and so Fricke and Klein, when they devote, in the first volume of the automorphic form, they devote maybe 50 or more pages to this equation. And at some point, they make a comment that this equation also appears in the formula of von Staudt for the volume of spherical triangle. So they look at the shape of the equation and make some connections, but never to Markov's equation. And it is quite striking because Klein in 1895, 1896 gave a course on quadratic forms, and it's published in, these are mimeographed notes, something like 600 pages. I have not seen reference to Markov's work there, but Klein was the editor of Mathematische Annalen when Markov's paper was published. So either this part of the book was written by Fricke, or Klein was really not aware of Markov's work, or both. Anyway, I think the first time the connection was made between this, between this identity and Markov's equation was only in the 1950s in the work of Kohn. I haven't seen references to that earlier. Now, the next result I will mention is.
Now, is there some connection between this thing, and continuous function?
Sorry?
What is the connection between disappearance and continuous function?
If I start answering, I think Bombieri's paper is really the best. The best. I cannot say it in one word.
Certainly, and also Frobenius's paper, who
Yes.
discusses quadratic forms and minima. Yeah.
And Markov's paper, if you.
Okay.
So Markov actually starts with, I don't want to get started. The Markov paper, the Markov thesis in Russian, and I went over it several times. I see no gaps, and it is very beautifully written. And he sort of starts from the beginning. There is a paper of Bernoulli. He goes to he quotes Legendre and Lagrange, and I think nobody else. And it's a very. I should be raising the tree. Let me. Okay. So I have not given a Blackboard talk, and it shows. The next.
Just for clarification, these two papers published in 1879 and 1880s.
This is in Mathematische Annalen, yes.
I remember they're both in French, so they are just the published version of his thesis, right?
I don't. So these are published papers. His thesis, as far as I know, was not published until So you can find his thesis and his collective work, which were published, I think, in the early 50s. And there is also, I think, on the 100th anniversary of his birth, which was, I believe, 1948. Russian mass surveys, успехи математических наук, they have a special issue devoted to Markov. And there it also appears. And if you want, I can send you the reference. But so I think at some point the Russian mass survey started being translated into English, but not done yet. So as far as I know, his thesis is only available in Russian, maybe also in Chinese. So the next, let me, so if I denote this variety by X, so the next, I'll skip some, but the next thing I want to mention is the paper. So the next question is, how many Markov numbers are there up to T? And it is a little surprising that this was not asked earlier, because Markov's academic grandfather was Chebyshev, and he certainly was aware of counting some sets of integers. But the first, so let me formulate this as a statement about the number of points in a ball on this variety. And the reason I'm doing it, I will not have time to go into it at all, but the answer here is quite different. So I will just and I conjecture that this beta n is transcendental for n greater than 3. But for n equals,
you might point out that's a theorem of yours and your co-authors. Recent paper.
yeah. So this is yeah. I do want to mention this result. I originally was thinking of spending some time on it, because this is I think the official title I gave was Arithmetic and Dynamics, and well, yeah. So this is a result which in weaker form appeared in author Barber's thesis, and then it's a paper of I guess I'm still the first author here. Yeah, McGee and Ronan. And it's asymptotic formula for integer points on Markov Curvatures varieties.
Is this compatible with what the circle method would say?
I don't think circle method would be applicable to this.
But it still make a conjecture in terms of.
So I'm not. Okay. So I started looking at what people believe to be true for integer points and varieties after we wrote this paper, and there are conjectures for rational points on varieties. This is, so I think this would fall into.
Here I was asking if you just wrote down a hardy little with heuristics, would it give this? It would give the, I don't know.
I don't think that Hardy-Littlewood heuristics would tell you that this. So this number ends up being related to certain projective measure with a fractional Hausdorff dimension. So I can tell you what beta is numerically. So basically, I'm going to state this result of Zagier, and Zagier proves this by comparing Markov tree with Euclid tree. And you have continued fractions and sort of Gauss map and Gauss measure, which is a full measure. When you start doing it in higher dimensions like Hurwitz and you linearize the equation, what you get is a semigroup generated by something like analog of continued fractions to higher dimensions. So the same semigroup actually appears in the paper by Chavray, I think, on reduction of ternary forms. But the set that you get is a fractal one. So I won't draw it, but see, that's where the I can give you the page. So I have not seen any references where this question of, so it's not, in this case, it's not quite the Hausdorff dimension of the limit set, but if you ask the same question, say for Apollonian packings, I haven't seen any papers where the question of algebraic nature of the Hausdorff dimension is posed or investigated. But here it comes up naturally because I think we can probably prove that this beta for n equals 4, this number is not integral and it is not half integral. And I personally am willing to conjecture that it is transcendental, not that it's, but well, I don't know how to prove it, but I'm also not sure how difficult it really is because I don't think people have thought about it.
Does it depend on the A?
No. So you can also put K here. So the exponent depends only on n. So for some values, okay, so for some values of A and K, you will have exceptional solutions, and in general, it is difficult to, even for n equals 3, once you put A and K, it's not easy to tell whether you have just one solution, and that's.
I think the basic answer is these are very Lacanry solutions. There are only logarithm number of them, and the Hardy-Littlewood prediction. It's like saying, would the Hardy-Littlewood prediction work on rational points on an elliptic curve, where there's the number of guys of height less than t is only growing like log? The answer is yes. That's what the BSD. That's how they found it. But I doubt it's true here. That would be too much to ask. But it does try to reflect itself even in a Lacanry thing. So this is how Burton Swinnerton and I discovered BSD. They computed the number of points and saw the log to a power. Then to predict the constant and all that, that's already, you have to analytically continue an L function. So this is.
I think one place where.
I think now you're getting sidetracked. If I may put you back on track.
My abstract was so vague that whatever I say.
That's it. Okay.
I wanted to mention about Hardy and Littlewood. One thing I'm going to get sidetracked once more, and then I will try to get focused. So there is an analog of this for 3 matrices, and it actually appears in one of Bill's papers. So there are trace invariants for 3 matrices, and you get a set of equations. And I think there actually it will probably just within Hardy-Littlewood. So what I'm saying, there are analogs of these identities for triple of matrices, and you get a variety, which I think would be just borderline Hardy-Littlewood in terms of counting. So let me get to the main. I didn't state. So this is about, I'll just focus on Markov from now on, and I'll mention what is true. And I should Okay, so here. So this is. So this result appears first in a thesis of Gamburd.
You did that
Sorry?
before Zagier.
Before Zagier. So this is in a thesis of Gamburd jointly supervised by Shapiro and Newman at NYU, and these days thesis is available on MassSciNet, and he obtains this result by comparing Markov tree with Fari tree. Zagier, 1982, and this is published. He obtains a better error term by comparing Markov tree with Euclid tree, and then there are results by Mirzakhani, and McShane-Raven, and a very beautiful proof is contained in the last paper of Belli. I think the best error term here to date, I believe, is log T.
P of T is a ball or a box?
A ball. So a ball of. So the only reason I stated it this way is to mention the result about Hurwitz varieties. What I'm actually counting, and what will be important for what follows, is a number of Markov numbers up to T.
But you can do L infinity norm as well, which is if you,
Yes.
You can use a maximum norm.
Oh,
Yes.
but the constant will be different.
The constant will be different, and the constant. So the constant actually has meaning in this case. So Belli, and this is the last paper before he passed away, he actually obtained, and it also is in McShane-Raven, the constant is basically the same constant, but it's a little bit more. So he obtains it as a limit of the volumes of convex polygons, and this is a volume of the ball of norm 1 in tacular space. So the constant actually has geometric significance. We don't know what it is in Hurwitz's case.
Is there even a constant? Is it not?
There is a constant. So there is a bit of an error term. There is a constant. There is a number. So I think beta 3 is something like, no, beta 4, I guess, is 2.7 ... But we don't know what is the geometric. So here, the constant actually has a deep geometric meaning, and you can ask whether this has a Hardy Littlewood asymptotics in the sense of Archimedean constant times, and I will get sidetracked. And well, I'll be here in the fall next year. So what's happening here? Yeah, so what I want to say is the Markov numbers are, so Markov numbers are sharp. Markov numbers are sparse. So n's Markov number grows like a to the square root of n. And I think I'm going to very quickly just say, so now I have to get to 2005 and briefly explain what the motivation was. And I did not know anything about Markov numbers until August of 2005, when I got a letter from Peter. I was coming for this program, and he wrote to me in August, saying that he has an interesting problem related to my thesis. And So there was a program there was a school in number theory in China, which Peter was organizing, and during that school, I think Philippe Michel and Akshay Venkatesh asked him a question which was related to the work they were doing with Einsiedler and Lindenstrauss, and related to Duplicate distribution theorem. The question they asked, translated into the language that I'm using here, is the following: are there infinitely many square free Markov numbers? Very clean. And the motivation came from the fact that, associated with quadratic irrationalities, there is geodesics, and they wanted fundamental geodesics, and that's why they wanted square free Markov numbers. And Peter had the insight that this question leads to the following one, which is still open. So if you look at this Markov tree and you reduce it mod P, you get a sequence of graphs, which we call Markov graphs. The question is, do they form a family of expanders? And that's why I got this note, because I looked at something similar related to Lubowski's 1, 2, 3 problem. I don't know. Yeah, as I suspected, people tune in to I think Ajdan is giving a talk today at the same time. So this is I only have half an hour, so I don't want.
Sorry, sorry to ask this in the middle of the talk, but this is an arithmetic group center. So
Say it again.
This is an arithmetic group center. So you
Is this a question?
Arithmetic group will appear in your talk. So that's what I.
Okay, I'll give you an arithmetic group. So let's take a look at the situation, which is okay. So this was a question which actually gave rise to what is now called a fine linear sieve. And it's instructive to very quickly take a look at that situation, which is in many ways, okay, so what makes this problem difficult is that this is nonlinear action. So let's take a look very quickly at a somewhat maybe I should start using the lower bracket to save time. Or maybe another way I can answer your question is that I guess this seminar is called Arithmetic Groups, right? So I guess my talk would be called but that I will actually sorry. So there is an example. So this is an equation which I guess you can call the Descartes equation. And this is the following. So what is this an equation for? So there is a result of Apollonius that if you have three mutually tangent circles, there are exactly two other circles tangent to this 3. And again, this is if you view this equation, so this is an equation for the curvatures of 4 mutually tangent circles. And if you look at this equation as a quadratic equation in x1, then you see that the two solutions are related simply as follows. So if you have one solution, you obtain another one by applying Vieta involution. But the transformation here is a linear one. So if you start with the involution here, it interchanges, it interchanges the blue and the red circle. So if you start with four mutually tangent circles whose curvatures are integral and repeatedly fill in the looms, then you get a configuration. Okay, so this is an initial configuration. You have the group generated by and you are looking at the orbit of A and the action of lambda. This is not quite an arithmetic group. It is a thin group of arithmetic significance. And in this case, we can prove that. Well,
that mentality and how they.
So this is an example which is very similar to. There's a lot going on.
It's probably the screw.
Yeah, there is a movie being made, and I mean, hello.
Should we bring them in here to take a picture of you?
Stop them from walking and say, I'm sorry, you have to wait until we're done.
Good.
No, I mean, this is real, this is serious movie, and that is just entertainment. So this is Institute for Advanced Study, and okay, so let me focus now in the remaining time.
Let me just finish your thought there. So that action there is linear, and you can do a sieve. You can sieve in quite general if you have a linear arithmetic group or subgroup of an arithmetic group. That's a general theorem. But to sieve here on this very sparse set, that's even. So when you sieve, you want to know what the solutions are for the even multiples of 3, multiples of 4, you subtract, and you add, do inclusion, exclusion. So in the linear case, we know how to do it. But in this case here, this becomes a much more fundamental question, and it's the question of what happens if you look modulo 5. And that already became a major problem.
Okay.
So so in this case, we can prove not only that there are infinitely many square-free numbers, but there are infinitely many almost prime numbers, so the numbers which are product of finite number of primes. And we can do that because we can establish this super strong approximation or expansion in the case of thin linear groups, which is still open. But another difference is that here, if you count the number of elements in the group such that the norm is less than t, this grows like t to the delta, where delta is the Hausdorff dimension of the limit set. By the way, I would conjecture that the exponent for Apollonian packings is also transcendental. So the set that you look at here is thin, but not nearly as thin as this. Okay, so let me state. So the problem we're looking at here is in the level of difficulty much higher than the case of thin linear groups. So these are groups which has a risky dense but of infinity index. But it is much simpler than, say, the case of tori, where strong approximation essentially amounts to Artin's conjecture. So let me state the result that I will not. So we cannot answer this. We cannot answer the. We cannot answer the question that was posed. I just get distracted. We cannot answer the question that was posed by
It's them.
Michelle and Venkatesh. What we can prove is the following. So we can prove that almost all Markov numbers are composite. And in fact, we prove that they're highly divisible. And when you first hear this result, it doesn't sound terribly impressive. Almost all numbers are composite, but even that takes a bit of a proof. So this was the second result that Euler proved after proving that there are infinitely many primes. So there are not too many primes. And if you look at the sparse sequences, it's quite difficult to prove a result of this type. So, for example, if you look at the numbers, which I guess one can call Cooley numbers, even assuming generalized Riemann hypothesis, which allowed Cooley to give a conditional proof.
What does that mean? HN.
So you look at this sequence of numbers,
What's that?
2 to the n plus b. And you want to prove that almost all of them are composite. So even assuming generalized Riemann hypothesis, which allowed Cooley to give a conditional proof of Artin's conjecture, is not. No, he had to make an additional hypothesis, which is something like Artin's conjecture for square-free module. So this is a consequence of strong approximation. Let me now state the strong approximation conjecture. And minutes. I will erase the tree, I think. And before I forget, this graphs that I'm talking about, they first appeared actually in Arthur Barger's thesis, where, so I mentioned that this was looked at first in the thesis of Barger, written under the direction of Joe Silverman, and it isn't counting points on Curry's varieties, but he also mentioned the graphs that are.
Just for Bill, the number there is the Artin conjecture is referring to is the baby Artin conjecture. That's is 2 a primitive root for infinitely many primes. Well, how often is 2 a primitive root? So if you take 2 to the n plus b, you reduce it modulo b. What does that sequence look like? And that's very tricky. And that's just one generator. And because the group's abelian, you have real problems.
So you get some generalized, so you need some generalized Artin's primitive root conjecture.
There's Artin's conjecture has been generalized for tori, but what Hooley needs, if you want to sieve, it's not enough to know what happens modulo p. You also need to know what happens modulo p times q. And then there's no theory that's useful. And so he has to just assume something that's self
I remember the best results is Higgs-Brown. So, but
So there's
That's
work
an Arkin's conjecture.
That's for Arkin, that there's at most 3 exceptions. That's Gupta and Murphy. But anyway, I think get back on track. So that's a torus. A torus is your enemy.
Where's the torus?
The torus is
Is
the
an
power,
enemy.
the powers of 2.
Well, what Peter is referencing is it in the context of a fine linear sea. So where you look at something like, so you look at the, so the general context of a fine linear sea is that you look at the group of affine linear maps, such as this one, which is the risky dense, but possibly of infinite index. And the general result, which, so there is a paper by Jean-Pierre and myself, and then there is a definitive paper by Peter and Alireza Sarahigel-Sevili. And the result there basically says that you have a finiteness of a saturation number as long as the group is Levy semi-simple. Saturation number is the following. So you look at the points in this orbit, and you look at the points such that they are product of a finite number of primes, and you ask, is there a number such that these points are risky dense? And the smallest such number is a saturation number, and you can also add a polynomial. But for tori, the finiteness of the saturation number conjecturally fails, and it is an enemy in this sense. And I don't think that there is an explicit. So in the context of a fine linear sieve, torus is an enemy, and it is an enemy also here. So we're sort of in between the enemy and so let me state that. So we are. So I've been talking about these Markov graphs, and let me define. So we're looking at this variety mode P, and I'm going to subtract this point 0, 0, 0. And this looks like a cosmetic. So these are vertices. So this looks like a cosmetic change I'm doing here, but in a more general situation, you first have to look at the finite orbits over C and remove them. And the more general situation is, for example, this one. So x1 squared plus x2 squared plus x3 squared is minus x1, x2, x3 is equal to k. Let me not write it down. I will state the results for Markov equation. There are more general cubic equations for which you first have to remove the finite orbits over P, and this is accomplished using Lang's GM. And so these are Markov graphs. So these are vertices. And you connect them, x to R1 of x, R2 of x, R3 of x. So we have the strong approximation conjecture. Asserting that these are connected. And we have, I guess, what one can call a super strong approximation conjecture, asserting that they are highly connected, that is to say, they form a family of expanders. And we started looking at this in 2005, and I appeared in the the graphs appear in also Vargas series, but the first time the conjecture appears in print is in the paper of McCullough and Vanderley called Nielsen equivalence of generating pairs of SL to P. And this conjecture is made in the context of product replacement graphs, which were mentioned by Alex in his talk in the fall. And let me very quickly review this. So the product replacement graph is something that used by people in computational groups here, actually in the real programs, I think Magma and the CAP, to generate a random element in a group, even if you don't know what the group is. So this is called the black box algorithm. And product replacement graphs are defined as follows. So, product replacement graphs defined as follows. So you have a group, a finite group G. So the vertices here are k-tuples of generators. And the edges are basically given essentially by Nielsen transformation. So you take G1, Gk, and you connect it to G1, Gi, Gj plus minus 1, Gk. And similarly, you define Lij. And this was looked at by people working in group theory thesis. But one of the first results, in fact, I think the first result, proving something about connectivity of these graphs is due to Gilman in 1977. And he showed that these graphs for SL to P are connected. For K greater or equal than 3. Now in 2006, Park and I proved that also for K greater or equal than 3 expanders, if SL2P is strongly uniformly expanded. So that is to say expanding with respect to all generators. And then Breuer and myself proved that this is true for infinitely many primes of density 1. And for n greater or equal than 4, these results are superseded by recent breakthrough that group of automorphism of a group for n greater or equals than 4 has property T, starting with the work of Ozawa, but the proof here is quite different. Now for k equals 2, you cannot possibly have connectivity because of the Fricke identity. So what McCullough and Vanderley conjecture is basically this. So the best you can hope for is that you will have connected orbits depending on the commutator, and that's what McCullough and Vanderley conjecture. I should mention that Gilman proves not just connectivity, he shows that the group acts as a full alternating or symmetric group. And using techniques similar to that of Gilman, Mary and Pura were able to show that in the cases where we prove connectivity, the action is as a full alternating or symmetric group. And that combined with Kursat's lemma allows you to move to square free moduli from prime moduli. And for the proof of theorem 3, that's what you need. I am really okay. Let me state what we proved. So there was a talk by Will, who proved that the orbit. So that okay. So the conjecture which I'm erasing, I didn't. So I guess the conjecture is the strong approximation conjecture for Markov graphs for prime moduli has been established. So I will state theorems 1 and 2, and combined with the breakthrough of Will, which he discussed last fall, this gives you strong approximation. The methods, I will state theorems 1 and 2. Theorem 2 I'm stating because it applies in more general setting where Will's results are not necessarily applicable. And I might not be able to state the result. Well, I think I might be able to. So theorem 1 is following, and and as I said, this is all joint work with Bourgain and Sarnak. So the first result says that these graphs have a giant connected component, which we call a cage, in the sense that, I guess it's a thing. So what is not in the connected component is very small. Note that the size of the Markov graphs is squared. The second statement here has been improved by Konagin, Markov, Polinsky, and Bourgain, but let me state what we prove. So every gamma orbit EP satisfies the bound that this is greater than log P to the 1/3, and they prove it to, I think, 7/9. The second result is the following. So let E be the set of primes for which strong approximation fails. And this set is also very small. So if you look at the primes in this is now theorem 3 was the well, I erased theorem 3, which was the statement that almost all Markov numbers accompanied will present it the proof of the result that every well, let me use the same notation. Every gamma orbit has size divisible by p. And now I have just 2 minutes, let me state them. Theorem 5. So theorem 5 is the following. So this is also a joint work with Bourgain and Sarnak. Assume that Markov graphs for prime moduli are connected. Then they're connected for all the moduli z mod t to the kz for all k. And then if you combine theorems 1, 4, and 5, you get the following statement. So for all sufficiently large p, gamma acts minimally on the p-adic. And I think I have to stop here. I'll be happy to take any questions you have. Thank you very much.
Right, as always, very entertaining. Any question from anybody?
Maybe I missed it, but you say what X minimally means?
Every orbit is dense. So I didn't have time to say anything about the proof. The proof actually has as a starting point an inspiration to Goldman's paper about the action of gamma on character varieties of one whole total. So the ergodicity there is proved using what is called dense twists, and we call them rotation. So minimality is a stronger. Anyway,
I think one way of saying it is Goldman studied the character variety. This is the character variety of the one-punctured torus. He studied this over the reals, and when the action is ergodic and when it's discontinuous, and what can happen. The interesting thing is if you go to the p-adics, XZP is always compact, and the action preserves p-adic integers, preserves integers. In that case, it's much more than ergodic. It's actually every orbit dense. And that contains every statement before. So it's really a minimal action is really a clean, I think, way of understanding. So the bottom line is the mapping class group wants to act on whatever its orbit is, it wants it to act in a minimal way. And in a way of the reals, that's your student Shah and yourself, maybe you proved something in the compact real component. It's stronger than ergodic. Ergodic is similar to there being a big orbit.
I think I think it is the super strong approximation conjecture over P and over reals that personally I think is the most exciting challenge in some sense for me.
Alex, can you hear me?
Yes.
Alex, may I ask you in a different direction? Can you I mean, I know that it's too early to even to start to conjecture, but if you, this is a very, very special case of something like, you know, a group acting on a scheme over Z or in algebraic variety defined over the rational over Z, and you see in the linear case, we know a strong approximation need simply connectedness. There are few obstacles, and if you pass these obstacles, then you have strong approximation. For thin subgroup, we can say almost always. Do you have any suggestion what can be a general condition, or when can we expect such strong approximation result, even before super approximation?
So I think Peter Wang, who spoke here in the fall too, I think he talked about relative character varieties of so this is a relative character variety of one function torus. He has a more general setting, which I think Peter would be able to say better, and that's one case where the methods would apply. Well, and also, for example, in Curvatures, so there are two parts to the question. One is where well, the question is what is my title was varieties of Markov type. So Markov can be generalized in a number of ways. I mentioned a more general cubic equations where we actually prove it.
Yeah, I think from a general point of view, there's a very interesting question. In the linear case, you take the Zariski closure of the group.
Yeah.
If you have a nonlinear finitely generated group of polynomial morphisms of affine space, what is the Zariski closure? Now, Shafarevich has a definition. He's got a definition which is something.
Yeah.
And I've often wondered whether one could start. So if you want any general theory, the first thing is you must take the Zariski closure.
Yeah.
And so when you have a nonlinear map, what is the Zariski closure of polynomial maps of affine space? So there is a very beautiful idea of Shafarevich. Apparently, he's assumed the Jacobian conjecture to make sense of what he's saying, but I've not seen it go very far. But I think that's where you have to look. First, define what you mean by the Zariski closure of a finitely generated group of polynomial maps. Then you can ask him for whatever that means, and he's got some filtration with some definition. And then maybe you can ask about strong approximation. I think it's a beautiful question.
Yeah. So
and this paper of Shafarevich should be looked at.
Yeah. So
I didn't know about that. Thank you, Peter, for the remark. I just wanted to say that's something which I find extremely interesting, and I have no conceptual even suggestion. We all believe in this Weigold conjecture that the automorphism group acts transitively on the representation if n is greater or equal to 3. On the other hand, it's known that for the mapping class group, acting on the representation of the surface group, the action is not transitive, and I would never guess that. Somehow I don't know how to separate between the mapping class group acting on the surface group and the automorphism group, the free group acting on the free group. Somehow.
And the property T, I think, for mapping class group is not known, if I'm not mistaken.
Yeah, no. I mean, I know, but don't. No, I'm not going to.
Because there was
relevant. No, property T is relevant for the super approximation. I'm not yet there. I'm just asking about the transitivity. I was very surprised to see this counterexample to the Weigold conjecture for the surface group. Somehow, and I don't see the conceptual difference.
I think we're just trying to understand some little examples. This is, I think, some things. Yeah, I will make people aware of Shaparevich's paper.
I think Shaparevich, I think he presented it first maybe in his talk at ICM in Nice. And he also wrote that I think his last paper, if you look at his archive, his very last paper in Russian is revisiting this notion.
Right. So I think probably we're all hungry, as you pointed out, and many of us have to get going. So you're here for the day, right?
Yeah.
So Alex is here for the day, and I'm sure he'll be very happy to continue discussing this with anybody. If anybody's got any further immediate question, otherwise you can just go to Alex right now. So
Are we going to lunch now, or?
yeah, we're now.
Well, except for the people.
But let me
Alex, good to see you.
let me officially end the lecture. Let's thank Alex again.